Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. K2-18b and the hunt for alien life. Signs in the hydrogen skies. In 2025, the exoplanet K2-18b, located approximately 124 light-years away in the constellation Leo, has become the focus of intense global interest, and for good reason. This distant world, orbiting a cool red dwarf star known as K2-18, lies within the star's habitable zone, the region where temperatures might allow liquid water to exist. But what's truly electrified scientists and the public alike isn't just its location, it's what's been found in its atmosphere. Thanks to the powerful instruments aboard the James Webb Space Telescope, JWST, researchers now have a detailed glimpse into the chemistry swirling high above this alien world. Whoa. Wow. Wow. With a mass about 8.6 times that of Earth and a radius roughly 2.6 times larger, K2-18b falls into a curious category of planets known as mini-Neptunes, larger than Earth but smaller than Neptune, and vastly different from anything in our own solar system. Yet despite its size and composition, the signals coming from this strange planet suggest it may be more familiar than we imagined. A strange mix of gases. The Hycean hypothesis. Back in 2023, JWST clearly analysis detected methane, R, and carbon dioxide in K2-18b's upper atmosphere. These gases are commonly found on planets with rich geological or chemical activity, but their specific ratio, combined with the lack of ammonia, sparked a bold hypothesis. Some astronomers propose that K2-18b could be a Hycean world, a newly coined term blending hydrogen and ocean. In this scenario, the planet is enveloped by a thick hydrogen-rich atmosphere, under which may lie a vast global ocean, possibly hundreds of kilometers deep. If the temperature and pressure at the ocean's surface are within the right range, it could host liquid water, the most essential ingredient for life as we know it. This idea was already compelling. But in early 2025, JWST detected something that pushed the conversation from speculative to explosive. The DMS debate. Is there a sign of life? During its deep spectroscopic scan of K2-18b's atmosphere, JWST identified molecular signatures of dimethyl sulfide, DMs, and dimethyl. Disulfide, DMZs, two sulfur-based compounds that are biologically significant here on Earth. Why does that matter? Because on Earth, DMs is only produced by life. It's primarily a byproduct of marine phytoplankton, microscopic organisms that populate our oceans. When they die or are consumed by other creatures, DMs is released into the atmosphere as a gas. If this gas were truly present on K2-18b, it would be a potential biosignature, a possible chemical fingerprint of life itself. DMDs, while less well understood in exoplanet studies, can also be associated with microbial metabolism and is often found alongside DMS in Earth's ecosystems. This led to headlines claiming, "Have we just detected alien life?" But the story isn't so simple. Scientific caution, a biosignature, or a false alarm. The detection of these molecules was tentative, and scientists have been clear. This is not a confirmation of life. The GWS data is incredibly sensitive, but interpreting faint molecular signals light years away is complex. Atmospheric models must be built, noise removed, and overlapping spectral lines, especially from methane, must be accounted for. In fact, earlier analysis in 2024 suggested the possible DMS signal might have been an artifact, an overlap with stronger methane absorption lines. But as of 2025, newer models incorporating multiple transits and secondary eclipses support the presence of DMs and DMDs with increasing confidence. While not conclusive, this represents the strongest candidate for a biosignature ever observed on an exoplanet. Oh, still, the scientific community remains cautious. There are abiotic, non-living pathways that could, in theory, produce DMs under certain high-energy conditions, or from volcanic chemistry, although none are known to match the efficiency of biological production until further observations, ideally across different instruments or with next-generation telescopes, confirm the signals with greater statistical certainty. The verdict remains open to a context. What makes it so special? Even without confirmed life, K2-18b is a scientific goldmine. It has helped astronomers validate JWST's exoplanetary tools, proving that we can detect not only simple molecules like water vapor or carbon dioxide, but complex organic and sulfur-based compounds in distant atmospheres. This dramatically advances our ability to evaluate distant worlds, and it's only the beginning. K2-18b also redefines the types of planets we're prioritizing in the hunt for life. For years, researchers focused on Earth-like rocky planets. But now, Hycean worlds, which may be far more numerous in our galaxy, are entering the spotlight. These planets may host deep subsurface oceans protected by thick atmospheres, offering a stable, warm environment for microbial life, even around dim red dwarf stars, which are far more common than sun-like stars. If life can arise in such settings, it could be much more widespread in the universe than we imagined. Zooming out, other notable exoplanets in 2025. K2-18b isn't the only world making headlines. 55 Cancri, a super-Earth about 41 light-years away, was also observed by JWST in late 2024. Though this planet is a blistering volcanic inferno with surface temperatures exceeding 2,000 degrees C, scientists detected a high-pressure atmosphere, possibly rich in carbon monoxide and hydrogen. It proves that we can characterize atmospheres even on small rocky planets under extreme conditions. K2-18b, once thought to be a rocky super-Earth, is now believed to be a water-rich mini-Neptune. JWST ground-based instruments revealed hints of water vapor and possibly clouds, suggesting the presence of a high-altitude haze. Its orbit around a quiet M-dwarf star makes it another candidate for future atmospheric biosignature studies. And in 2025, the European Aerial Mission has begun cross-referencing hundreds of exoplanet atmospheres to build a planetary climate map. But this effort will deepen our understanding of which planetary classes can retain water and carbon-based compounds, and how star type affects planetary evolution. The bigger picture. What K2-18b means for us. The story of K2-18b, its gases, its ocean hypothesis, its possible hints of life, is not just about one planet. It represents a new phase in the human search for companionship. In the cosmos, we're no longer asking, are there planets out there? We're now asking, do any of them breathe? And even if K2-18b's signals are eventually proven to be false positives, that's still a huge step forward, because every failure to confirm helps us refine our detection methods, sharpen our instruments, and improve the models we'll use for planets even more promising in the future. JWST has proved it can peer into alien skies and read their chemistry. The challenge ahead is making sense of what we see. In the next few years, with telescopes like LUVOIR-HABEX and the extremely large telescope, ELT, coming online, we may not only detect biosignatures, we may discover entire biosphere. And when that day comes, K2-18b will be remembered not just as a distant planet with strange chemistry, but as the first place we ever whispered, maybe.